that I think when you download the file from D2L, it will be a zip file, and you'll just have to figure out how to unzip that. Usually double click on it on your computer, and it should unzip the file. And then, in my case, I can just double click on it, and that syntax will open up in SPSS and look like this. In your case, you might have to do file open syntax, and then point it to that file. And then open it up if your computer isn't configured to automatically open .sps files with the syntax editor, okay? I know Apple is by default. I can't speak to PC computers. So we're going to talk about what we do with this syntax here in a little bit. But before we do that, I want to talk about what parallel analysis is. So it helps us to identify the number of components to extract. It's another method. I think it's probably the best of the three, so I'd weight it heavier. If the other two, the scree plot, you couldn't quite decide on, the number of eigenvalues greater than 1, if that wasn't quite, maybe you had one that the eigenvalue was 0.99998. SPSS isn't going to extract that value because it's less than 1, and it's only extracting values greater than 1. So if you had some, if eigenvalues greater than 1 isn't concrete, this is, I think, a useful way to try to get at the number of components to extract. So it's a looping process or iterative process that we randomly generate a data set with the same number of cases and variables that you have in your data set. So we use SPSS, and we say SPSS just generate random. It's actually pseudo-random because there's not a random number generator. It's a pseudo-random number, but random enough for just about every purpose. We tell SPSS to generate a random set of data that has the same number of cases that you have in your data and the same number of variables that you have in your data. And then it performs a principal components analysis on that data, and eigenvalues are noted. So each time it does that, it keeps track of the eigenvalue. And then that process is repeated some number of times, 100 times, 1,000 times, 10,000 times, whatever number you want to put to that. With my computer, it used to be 10,000 times would be do it before you walked out of the office at night and hoped it didn't crash by morning, and it would be done by the morning. But now modern computers can do 10,000 in less time than it takes you to get up and get a cup of coffee. So it's probably 15 seconds or 20 seconds to do this 10,000 times with my laptop. And so then what we do is, this is all just random data, right? It's just so-called junk data because it's just random numbers that have been generated. And we perform the principal components analysis. We take note of the eigenvalues, and then we look at, well, what's the mean eigenvalue for the first component? And what's the eigenvalue at the 95th percentile? And this is just randomly generated data. And so we compare our good data, hopefully it's good data, with this randomly generated data. And if our good data isn't better than the randomly generated data, you better not use the good data, right? Because we need to be, if our components aren't explaining more variability than just randomly generated data, then you better be pretty careful about saying that this thing is meaningful, because it really probably isn't all that meaningful. And so
it's just like setting an alpha level at point. It's the same thing.
It's sort of synthetically generating data that allows us to set the alpha level at the 95th percentile or point, one-sided test at 0.05. Yes, but it's a synthetic process in that we're generating this data in order to get us at that. We wouldn't be able to get at this without that generated data.
Going back to what you were talking about before, the eigenvalues, the output gives you, like, are you looking at the total one and that has to be?
We're going to look at the eigenvalues for each of the components. And I'll sort of show you in a minute which eigenvalues I'm referencing here. I really haven't pointed those out. We haven't even looked at that table yet, but we're going to get to that in just a minute. So I'll show you exactly which eigenvalue, and it's the eigenvalues that are associated with each of the components. And then there's a total as well, but it's the ones that are associated with each component. So the comparison is, once you see it in the abstract, hopefully it makes some sense. And then once you sort of see how to do it, I think it will make a little bit more sense.
So those are different from the ones that we did before.
Which ones did we do before?
For whatever reason, I don't have the slide on here. I didn't print out. I'm missing like 2 pages. But it was like 2 slides ago, and you said that the eigenvalues represent the variance.
Yeah, it's the same eigenvalues. If it's these same eigenvalues that we plotted here.
So it has to.
And it's actually these eigenvalues right here.
So that is the plot is plotting that.
Yeah, so that plot had 3.04 for, and it is the title of the column is total, so that was a little bit misleading. But under initial eigenvalues, total, component number 1 is 3.004, which is this point right here, okay? And then this is the second component and the third component, and so it just... Did I answer your question, Jackie?
Yeah.
And so I think once you see the output and sort of look at it, I think it's fairly intuitive. So let's look at the data. Let's look at the data that I have and figure out what was the n. The n was 320. I think n was 320. And how many, after I excluded a number of independent variables, I ended up with 15. I excluded some because of low communalities, and I started with 17, deleted 1 because of the skewed. That brought me to 16. I deleted 1 more because of low communality, and then I think I have 15 as the number that I'm going to work with, okay? And so what I need to then do is when you open this, all you need to do is how many cases do you have? And has anybody opened this file yet? Does it have the question marks there?
Yeah.
Okay, because in some earlier versions, I typed over the question marks. But so you just fill in the question mark with your n, your number of variables. In my case, I'm going to do 15. Uh-huh.
So this, when we were entering this in, this will apply to any data set that we have open? Like that's how it works?
This doesn't even need to have a data set open because it's just going to generate random data.
Oh, okay.
So it uses random number generator to generate data. So you can run this without any data open, or if you did have data open, it wouldn't be paying attention to it, okay? And then you can tell it how many iterations you want it to, or how many data sets you want it to run. And I'm saying 10,000. Don't make it 100,000 because that might take a little bit. 10,000 is like way more than you really need. 1,000 probably is a good number, but overkill is probably better than under.
If we're not using a data set that's in there and we're just generating random data, why do we need 320, let's say, as n?
Because we want to have this synthetic data that's generated to be comparable in size and scale, meaning number of variables, as the data so we want the matrix to look the same.
Okay.
at least in dimension, as our matrix looks, although this data will just be noise because it's random. Okay? And I think SPSS likes you to highlight everything and then click play. And so you can see that it's running, and it might take a few seconds for it to finish, and then it's done. And the output, I've got too many windows open here. And then so this is what the output looks like. And this output won't match the output that you have in front of you because it's random. They're randomly generated. It's going to be close. It's going to be within, good enough for the government, right? It's going to be off by 1,000 or tens of thousands probably at the most. But this is the output that it's going to produce. And then we're going to compare. This is so for the first component, for 10,000 iterations, the mean was 1.38, and the 95th percentile is 1.46. Well, if our first component isn't at least 1.46, we're not doing very well, right? And our first component was what? 3.02, right? So we're well above 1.46 with our because this is just random noise, and our data is well above the 1.466 because we're at 3.02, right? So I'm going to flip back to this, which should be very close to what I just had on the screen from the output. The only difference would be the differences in random numbers that were generated. And the comparison that we're going to want to make is with this column that we have right here. And so eigenvalue is greater than 1. It extracted 6 components, yeah, because this one here is 1.017. So that's the default in SPSS. It will extract components where eigenvalues are greater than 1. We already looked at the scree plot. The scree plot isn't all that helpful in understanding the number of components extract. Now we'll look at the parallel analysis. So this is 3.004, not 3, and this first one here is 1.47. We're definitely greater than it, so we can have some confidence that this component is meaningful. The next one is 1.72. 1.72, and this is 1.35. Good or not good?
Good.
Good, yeah, right? Because our number was, why do you say good?
It's greater than 1.35.
Yeah, we have 1.72. I have to get my arrows right. I'm sorry. We have 1.32, and this is
1.72.
1.72, and this is 1.35, and 1.36. So we're greater than it. So we can have some confidence that our second component is not just chance, because this is just random chance that generated these numbers, right? It's not. There's no mechanism generating the data other than a random number generator. There's no thought that's being put into it. Our third component is 1.28. And the third here is 1.28. So pretty close, right? I think I would probably be okay. It's close enough to at least sort of look at it initially. And then the fourth is 1.15? And the fourth here is greater than our data, right? So the random number at the 95th percentile is greater than our data. And in fact, the mean is greater than our data too, right? So how much confidence should we place in that fourth component being a meaningful component? I wouldn't put very much faith behind it. If we were to repeat the study, different sample potentially. Who knows whether that fourth component would be above 1 or below 1. So the process is simply matching up your components with the synthetic data, and where your components are greater than the 95th percentile, you can have some confidence that your component's meaningful. Where they're lower than the 95th percentile of the randomly generated or synthetic data, one needs to be very careful about interpreting that as being meaningful. It's as meaningful as randomly generated data, which isn't very meaningful, right? So in this case, we would come up with 3 components, I think, would be the comfortable conclusion. Eigenvalues greater than 1 come up with 6 components. Did Cameron come up with 3 components on Screeplot, or did somebody else? Huh? So we can sort of converge on 3 as being the, where's my Screeplot? I'm going the wrong direction. So this is, did you say 2 or 3, Cameron? Do you remember?
I think I just said 2.
You said 3?
Yeah, I said 3, yeah.
So one expert in the back of the room, and then the parallel analysis both converge on 3. The eigenvalues greater than 1 gives us 6. Choose the evidence that you think makes the best case for the number of components. I would go with the 2 that converge on 3.
You were way off with saying 13.
I was way off when I said 13, wasn't I? But that does seem more like to me where that thing. If we were to mathematically measure those angles all the way along the line, and this is going to be the angle that is closest to flat. So 13. So far, good enough. Adam?
Are you gonna, I guess my question is, how much do we need to report of this in a manuscript? Because I'm thinking of our article I've never.
You can look at what I report, and it's a sentence that covers really all 3 of these. And I say something very similar to what I just said, that although I think at the end of the day we end up with 2 components, but you don't have to put much effort into, or you might have to put a lot of effort but not a lot of words into it, a couple sentences at the most. And it's not even though your textbook talks about it as being probably the, I don't know, she doesn't say the preferred, but they certainly put a lot of emphasis on it. It seems very intuitive to me. It's not used very widely, and I don't know the reason why it's not. But I would encourage you to sort of think about incorporating it. But it doesn't have to be 2 paragraphs devoted to parallel analysis. It can be really a couple sentences ought to cover it, and the Screeplot and the eigenvalues greater than 1. You ought to be able to easily, because all you want to discuss is how many components are you extracting, and how did you come to that conclusion. And you might have used just Screeplot, you might have used just eigenvalues greater than 1, or you might have used all 3, including parallel analysis, and it just wouldn't take all that much to write that up. Okay? Other questions?
So, just overall, kind of what we're saying is, out of the 20 questions that we had to measure this, there was only 3 main
Components.
that came out of that those all kind of cluster around 3 different things
That's it.
that have meaning.
That's it. That's the conclusion. Well, that's when we're talking about the number of components to extract. That's the question we're trying to get at. How many groupings of variables are you going to have? Are you going to have 13? Are you going to have 6? Are you going to have 3? That's a very important question, because if you say there's 13 dimensions of source credibility and somebody else says there's 3, there's a big difference there, right? And so depending on how many components you decide to extract and the criteria you use will make a big difference, and could make you look very smart, or could make you look, you said 13, maybe not so smart when somebody else says, no, that's just not, 13 is not a reasonable number. You only had 16 variables in the analysis or something. So far, so good.
Quick question off of what you said. So if there's only one, that means you're measuring the same.
Yeah,
They're
so
all
you got, is that what you end up with?
Yeah.
They're all correlated highly together, and
So I
they,
knew that to begin with.
right, but we don't know that until you run it, and so you have to come up probably with some different data, because they're all correlated together and they don't group in any way. But I'll be happy to look at it. There might be something we can do to, but there you come up with a single factor. It extracted one factor.
Yeah. So,
Yeah.
I mean, without, so if it extracted two, that would mean it's kind of measuring two different things.
Yeah.
But don't you want it only to be measuring one thing?
If the thing that you're studying is unidimensional, then you'd only want it to measure one thing. But
For those things that you're studying.
I don't know, what are you studying? I forget what it is.
Marital happiness.
Is marital happiness unidimensional? Is there? I think there's several dimensions of marital happiness, right? That it's not all about sex or money or good food that somebody cooks, right? It could be those and so I don't think it's
Maybe one more.
unidimensional. Yeah,
Right. So that
your data suggests that it is though.
Right, and that's not good.
Like at least two.
Did you say that?
No, these are like happy, strong,
You say
stable.
that every time you hear vowels.
I mean, that makes sense.
Yeah, but we'll have to talk about it, or I'll be happy to look at it after class and see if there's a way around it. But it might be where you have to come up with a different set of variables because that's not. So I think that's useful thing to keep in mind. If you do your analysis and it comes up with a single component, send me an email, and I'll send you some new data to work with. Okay? Because that's you sort of end before. You're only like halfway through, or maybe 2/3 of the way through the process, and there's not a whole lot more you could do. If this was research you're working on, that may or may not be a bad thing. Maybe if you think the thing is unidimensional, then that's a good thing. And I've seen people report that before, that they did exploratory factor analysis, everything loaded on a single dimension. That's what they expected. I would have done confirmatory factor analysis in that case instead of exploratory, but. So there, in a research context, that might be a useful outcome.
Then wouldn't the opposite also be true if you're measuring whatever and you have 13 variables and you get 13 and they're all measured?
That's then right. Then there's no parsimony there that's going to be had, right?
So is there like something that, is there a number that you should be looking for, or that's totally?
Some number less than the total number of variables you have, and some numbers greater than one. But I don't know. I like 3 is a good number, but that's just because 3 is sort of a good number for a lot of things. But 4 would be good. 5 would be good. So there's not a black and white. Sorry.
But if you're choosing 6 variables, then shouldn't we be looking for 6 components?
If you're working with 6 variables?
Yeah.
No, if you're working with 6 variables, you wouldn't want to have as many components as you have variables. You would want to have fewer components than you have variables.
Wait, because I have this, it's an ethnocentrism measure, it's supposed to have 6 dimensions. There's 36 items, but it's factoring at 7 components, and it should have 6.
The theory, whoever came up with the theory, said it should have 6. They probably tested it, and it had 6. Your data using exploratory factor analysis has 7. I don't know if that's a problem with the theory or a problem with your data, one of the two. But I would probably actually, as I indicated earlier, I think, I would do confirmatory factor analysis with that because they've already, you just want to confirm what they have found, that there's 6 dimensions, and that's partially what leads to the problem. If you did confirmatory factor analysis, it might fit perfectly fine. When you let everything co-vary, that's when you came up with. But I don't know that shouldn't stop you from using that data for your analysis.
Okay.
Right?
Yeah.
because they said there should be 6. You have how many variables?
There's
36?
36 items.
36 items.
Broken into 6 variables or 6.
And you did the factor analysis on all 36 items.
Yes.
And it came 7 factors.
Yes.
But maybe, and all 7 factors have eigenvalues greater than 1, I assume. Then you look at the screen plot, and then also you could look at the parallel analysis. Maybe at the end of the day you'll decide you need to have some number other than 7, 5 or 6, or it probably would be greater than.
Maybe you need to write a paper and say that the theory needs to be extended. No?
All right, so other questions that I can answer or not answer?
Well,
Brianna, yeah, let me try not to answer this question.
can use like when you can use principal components or EFA to kind of determine if it is unidimensional or multidimensional to help you determine how you're going to score your compute variables out of that to run an analysis.
If you wanted to just, is this unidimensional, you could run EFA. I personally would do CFA and just see if it all loads in one dimension.
But if you don't know that.
Oh, if you don't know,
Yeah.
then you do EFA. Yes. I thought you were knowing that it was, yeah. So if you have a hypothesis about how they should load, or strong support from past research, CFA would be the better route to go. But we're doing EFA. But for this class, you do just use the data that you have, even if in practice you would use a different approach.
Because I'm thinking of scale development. So you write new items
Yes.
and you don't know.
That's a very exploratory process, right? And that's where EFA is hits home runs, right? That's you can't use CFA in that context because you would be guessing, and it's a confirmatory process. Michael.
So, say it comes out, you have 3 factors that everything else loads onto. Then, as part of your paper that you're writing, your manuscript, do you name each one of those and say? So, I mean, kind of you're saying here are my codes, or that's
Yeah,
kind
we'll
of the
talk about that.
quality.
Yeah, you definitely name those components or factors, or that's the traditional way that it's done, and it wouldn't make sense to not try to do that. And we'll talk a little bit about the art of naming principal components or factors, because it really is as much of an art. As much of this is, as I said earlier, it's a data exploration. It is a process that moves in a lot of different directions, and you have to make a lot of different decisions. One being the number of components to extract. So far, so good. Other than you try to do your, Michael.
So would this be considered inductive?
I would say it's certainly more inductive than is confirmatory factor analysis, which is clearly deductive. And like a lot of inductive research, you're not approaching it sort of empty-minded, right? You wrote some questions with some ideas in mind, and now you're going to, you have no idea sort of how they're going to group together. You might have some intuition about how that would work, but you're going to use software to help you figure that out.
I like it.
All right?
So therefore, in this table we have 6 factors,
In this case, we extracted 6 factors, yes.
and in this table we have 3.
Yep.
So which one we
And
should-
Cameron said 3 too. So we had 3 from Cameron, 3 from the
random there?
that one. So I'm going with Cameron so I'm going with Cameron and the parallel analysis, and we're going to extract 3.
What if those are completely different though? So what if you're in parallel?
Yeah. Then you'll have to. So what if the parallel analysis said 3?
What if that says a lot more than what everything else that you do in SPSS?
Then you'll have to use your best judgment about what to do. And but that's what it is, right? It's and then at the end of the day, we're going to get to a point where you have to try to make sense of the factors or the components, and if they don't make sense, then you'll know, well, maybe I should have tried the other way. So let's say we had 3 from the parallel analysis, and this came up with 6, and let's say we just happened to say 4 from the discrete plot analysis. We thought 4 was the best number where that line finds out. So they're all different numbers. Pick the one that you have the most confidence in. I would pick the one from the parallel analysis, just because I have the most confidence in that procedure. And then you're going to complete the analysis, and you're going to try to interpret how those scores load, or those variables, or those items load. And if you can't make sense of it, then you can backtrack and say, okay, maybe it should be 3, maybe it should be 4, or maybe it should be 5. And there's nothing wrong with doing that, because this is data exploration. It's not a deterministic process. It's a exploration with the data, and if one thing doesn't work, you can go back and change and see if you can come up with something that works better for you. But that will often be the case, where the parallel analysis, the discrete plots, they all come up with different numbers. And so you'll have to determine which one makes the most sense to you. I personally would use the parallel analysis when in doubt. But that can lead you astray too, and you might have to go back and try to fix some things. All right? Other questions? We're good? For the example data that we're working with, the analysis was rerun, but this time I told it to only extract, this is the, under the extraction box, I told it to only extract 3 factors. Instead of what it did is eigenvalues greater than 1. I said no, do only 3 factors. 3 based on the parallel analysis and on the discrete plot analysis, right? Make sense? Rerun it. After rerunning the PCA, and this is just the example that we've been working with, after rerunning the PCA that extracted 3 components, I had to remove 6 variables. It killed me each time I had to go in and remove, because this is a lot of hard work that actually it wasn't any hard work that I put into it. But if this was work that you were actually doing, and you actually wrote these questions, and you actually collected this data, it would be, this isn't painful, but I've been in that position where these questions just aren't working. They don't hold together in a way that I thought they would. And so I removed 6 variables one at a time because of low communalities. And either, I've said this a couple times, either we remove them at this step, looking at the communalities, or we're going to remove them later because they're going to be cross-loaders, and they're going to load on multiple components. So either you do it early or you do it later. My preference would be to do it earlier, so when you get to the final solution, it is a little bit easier to look through. I had to redo the parallel analysis in the discrete plot, because I removed the 6 variables, right? So my parallel analysis was no longer, I had 15. I had to change that to 9. And the n was still at 320, okay? So I had to redo that and redo the discrete plot. And this is these are the 2 tables that will help us to understand the number of components. So I'm still saying 3 components, and I do in fact have 3 components where eigenvalues are greater than 1. And you can't see this very well here, but you can see it on here. How many components does the parallel analysis tell us I can safely extract? How many? 3? Why 3?
Eigenvalues greater than 1.
1, 2, and 3 is greater than 1, 2, and 3 here, and 4 is greater here than it is there, right? So does making sense of the parallel analysis output make sense? Okay? So the next step, we've sort of cleaned up all of we've ran the analysis. When I deleted these 6 variables here, I ran the analysis 6 times, each time deleting one variable at a time. Of course, don't give me all that output. You can give me a summary that looks about like this, and that works good enough for me.
What, I don't understand why, so you wouldn't know until after running the first ECA about the low commonalities? Like, because remember we talked about removing.
Yeah, I removed one, and then when I changed it to, I decided that the number of components should be 3, not 6. They were using 6 here, and it was that change that I made that led to this. I could have kept 6, and I could have had 6 components that I looked at, but they wouldn't have made any sense, and there would have been a whole bunch of cross-floaters. So again, I think this would be the safer. I don't know about safer, but I would get rid of them at this stage, and that's why it changes, because I had to tell it 3 components, not 6 as it was doing. All right. So now we need to interpret our solution with oblique rotation, which is the type of rotation where we're saying that the components are correlated. It is most useful to examine the factor pattern matrix, or just pattern matrix, I think is how SPSS refers to it. If you use orthogonal rotation, the rotated component matrix is what you should interpret in terms of understanding the solution. And so these are just different names given to different pieces of output. And the interpretation is we're going to start with the left-hand column, or the first component, and then we're going to move right. And then the component loading criteria, it's again not black and white. It's a matter of preference. People's experience has a lot to do with how they make this interpretation. A simple criteria is to examine the matrix loading for items loading greater than about absolute 0.4 to make certain that each item loads on one and only one component. So if you see a variable that's loaded at 0.5 on one component and then 0.56 in another component, we know that that variable is cross-loading and it's loading. So we want it to load greater than approximately 0.4 on one and only one component. Items with 2 or more loadings greater than absolute 0.4 are considered cross-loaders, and you'll have to delete those from the analysis and then rerun the analysis. Hopefully you won't have too many of those at this stage if you sort of follow the steps and eliminated variables with low commonalities and eliminated variables with low MSA measures of sampling adequacy indicators. So that's one criteria. Another criteria that you see is approximately 0.6 as a general threshold. But if it loads approximately 0.5, if it's not loaded very strongly on any other variable, and by very strongly, something less than about 0.3. And items with component loading greater than 0.3 on 2 or more components and no loadings greater than 0.6 should be considered cross-loaders. So either one of those criteria, at the end of the day, will probably get you pretty close to similar results. I always just start with 0.4, and that's usually does 90% of the work. And then sometimes, if I'm not sure about whether a variable is on a loading clean line component, I might sort of remember that. Well, let's look to see how strong it loads on the other component. So this criteria can come into play.
If you have one of those that is a cross loader, then probably it's pretty important to both of those. I mean, I don't know. It just seems weird that you just delete it, because it would seem like it'd be kind of a valuable piece in understanding that those two factors.
But if we're trying to understand the example of source credibility and leadership, and let's say leadership is one of the dimensions of source credibility. What's another dimension of source credibility?
Trustworthiness.
Trustworthiness. And if we have something that's strongly correlated with, I mean, is leadership and trustworthiness two different things? Or are they the same thing? And I think we would say that, well, they're probably, somebody can be a leader and not very trustworthy. Somebody can be really trustworthy, but maybe not have the leadership skills. And so if something loads equally strong on both of those, I don't know how that's important. I don't know how that's important. Huh?
So
It
it's
doesn't
not
help you
helping us to
It,
differentiate.
it absolutely doesn't help you to differentiate.
And
and I
that's our goal, is to differentiate these two
Yes,
factors.
we want to have a set of variables on multiple components that correlate strongly amongst each other, and relatively weak correlations between the other components. So reference this page frequently as you're trying to make sense of. In the abstract, it doesn't make very much sense, but when you flip to this screen and we apply that criteria, I think it will make a bit more sense. So just remember that these are correlation coefficients here, really, and it's a correlation between the original variable and its component. And this is component 1, component 2, and component 3. Okay, so think of them. And so in this case, this variable that R feels like a selfless caring. R feels selfless and caring for others. It correlates very strongly on this component, and then it correlates very low on component 2 and component 3. Why are there no numbers for 2 and 3?
But it's not significant.
No. Anybody want to take a guess?
It doesn't fit at all into them.
I think that's close. Remember, in the setup I told you that what I would do is only display values that I would say suppress small coefficients, and this is the default at 0.1. So if the value is less than 0.1, it just won't print anything now, okay? And so you could set this at whatever value you wanted to, but 0.1 just sort of, and you could print those if you wanted to, and it probably wouldn't matter all that much, but so this question here loads pretty cleanly on greater than 0.4, right? If we use that criteria, greater than 0.4 on greater than 0.4 on one component, and then nothing even close to 0.4 on the other two components, right? The second variable, pretty good as well, right? Third variable, okay. Fourth variable, okay, right? So these first 4 variables load on this component number 1, unnamed component at this point. Variables 4, 5, 6, 7. Okay, right? And then variables 8 and 9, if my math is right. Are they okay? Yeah, if we use that 0.4 criteria, they load fairly strong here, and nothing is greater than 0.4 on component 1 or 2. So that would be a solution that one could start with in terms of trying to make sense of those 17 variables that we started with. However, a couple things that are important criteria to keep in mind. Usually if we have single item component, so let's say this question here by itself that somebody did volunteer work, loaded all by itself on its own component. The general way of handling that is to unfortunately just delete it. Because it's not very well defined, right? You have a variable that loads all by itself on one component. It's not very well defined. Next time you do a data collection using that scale, maybe you can write more questions that sort of get at that idea of what that thing was, and then maybe you can include it in subsequent analyses. But single item components are generally frowned upon, especially in this context. To say that, I started with 17 variables, and this one variable is this thing all by itself, probably in most places won't get you very far because it's just not very well defined, and you were doing exploratory work to begin with, so it seems reasonable to continue that exploration and try to develop a greater level of understanding about that, why that single item was by itself. Two item components are slightly better. With two item component, the reliability depends on the correlation between the two items and the correlation between the items and the rest of the items. Generally, for two item component to be meaningful, the correlation between the items should be greater than about 0.7. That's not a black and white. That should be an approximate. And correlations with other variables should be reasonably small. If we look at a correlation matrix for my two item solution, the correlation between those two variables, these two variables here, somebody gave money to a charity and somebody did volunteer, the respondent did volunteer work for a charity. The correlation between those two are relatively low, 0.381, right? So not even close to 0.7. And so the thinking there would be, again, it's not very reliable, it's not very well defined given the low correlation. We probably would want to remove those two items and rerun the analysis. And so that's what I did. Instead of extracting 3 components, I only extracted 2 components. And I ended up with these 2 eigenvalues, reran the parallel analysis, reran the scree plot, and came up with this solution where I have these 4 items. How the respondent feels, that the respondent feels selfless and caring for others, that they like to assist people in trouble, that they accept others even when they do the wrong thing, and that people should help the less fortunate. Those are strongly correlated. People who have high scores on those tend to have, on one of those tend to have high scores on the other, and they tend to they tend to be uncorrelated with people who said that they gave their seat to a stranger on a mass transit, that they have given food or money to a homeless person, or that they carried a stranger's belongings. And so,
Well, because it's like those are behaviors and the other ones are perceptions of their own behavior.
Yeah, and so that would be
You just named them.
yeah, that would be the criteria. That would be the thinking you'd want to put into how you name these things. And so some people actually do things to they're altruistic they have altruistic behaviors, right? Other people have altruistic attitudes. I'm not saying I'm not judging one as being better or worse than the other, but if we sort of look at the data, that's the outcome that would make sense to me. Jackie?
So the other criteria from before, it was saying like if that was, so people should help less fortunate others, that was saying like, if that was point, if those two are closer together, that would mean they're
Yeah.
doing the same thing.
So let's say this was 0.4 and this was 0.35. I'd be like, damn, I gotta do it again, right? You delete this variable and you'd probably run the thing again, right? Hopefully, if you get rid of all of the low MSA values and all the low commonalities, you have sort of a minimal amount of that you have to do at this point. But you're either going to do it here or you're going to do it earlier in your analysis. And if we wouldn't have done it earlier, we would have had 6 components and a bunch of stuff would have cross-loaded and we would have deleted items one after the other.
Taking more time.
I don't know if it would have taken more time, but it doesn't seem like the right way to do it. For me, I would rather, before I get this to this point, I'd rather get rid of the noise and stuff that doesn't work. And then remember, if some of these are negative when you do your analysis, what does that mean? They need to be reverse coded, right? They absolutely need to be reverse coded. That's the only reason why. Some of the lower numbers can be negative, but if let's say this was minus 6.53, that variable absolutely would have to be recoded. There's just no other reason why. It would load so high, and have a negative relationship. So you'd want to go in before you sum these together, if that's what you wanted to do. You'd want to go in and reverse code that one. All right? So you would use your experience, your perceptions, your expertise, and all of the creativity you can muster to come up with names for these. The procedure that I use is not very, it's more mechanical. I tend to look at the item that loads highest, and that's the one that I would probably rely on most in terms of trying to name a particular component. And I don't know, I think at the end of the day, these definitely are behaviors, and it wouldn't matter which of the 3 you looked at. These are more perceptions or attitudes that somebody would have. So this would be a step that you'd want to eventually get to. Give some names to these. And what do I say? Active altruism and selflessness, or whatever. I mean, you name it. It's your data. You'll name it whatever you want to name it. And you have to make it sound academic, though, right? The name is sort of some of the marketing, and so I would try to think and rely on past research to the extent that you can to come up with names that are meaningful and names that will be meaningful for people that read this literature. These names aren't. I don't study altruism, and so these are just sort of everyday terms that I think people would use. So far, so good? Questions? So let's go back and before we're done, let's go back and look at homework number 4, which is the one that's due not this week, but next week, right, the 25th, and see if there's any questions that emerge from homework number 4. So I'm asking you to do principal components analysis, a minimum of 6 variables. You need to examine your assumptions for factor analysis. All of that makes sense now, more sense now than it did 2 hours ago. Questions? You're good? Everybody be able to do that? I would encourage you to do it. Don't wait till Friday the 25th at 4:30 to make. If you do make an appointment with me, I'll be happy to visit with you if I can. but I would hope that you are working on this, especially given all the details that you have to keep track of. The last couple slides sort of answer the question, what do we do next? So after you do your factor analysis, and you come up with your factors, what are the next steps? Oftentimes we use summed scales. And so we are summing the scales together, maybe taking a mean across individuals. In our case, because some of our variables were measured on 1 to 5, some of them were 1 to 7, before we sum those together, I think we want to standardize them. Because if we didn't, what would happen? If we had some that were 1 to 7, some that were 1 to 5, and we summed them together, what would happen?
It's going to skew it
Skew it in what way?
positively. Right? So if you have some that are 1.7, the ones that are 1.5, it's going to be like, well, this is a 5.
The variables that are on the 1 to 7 scale potentially will be weighted greater in that sum scale than the ones that are on the 1 to 5 scale. So the best way to fix that is to just standardize the measures and then sum them together. We should calculate Cronbach's alpha. We should calculate Cronbach's alpha, which, if you remember right, didn't we do that like week 1? Week 2? Does everybody remember how to do Cronbach's alpha? So you can do, let me find my mouse, you can do analyze, you can do scale, and you can do reliability analysis, okay? And then you just put in our case, we'd put the variables, and I don't remember what the 4 are, and I don't want to take the time to pick out the 4 that loaded on the first component, but we'd put just the 4 variables that loaded on component 1 in here. We'd get the reliability, and then we'd move those out, and we'd put was it 3 that loaded on the second component? Or 4, whatever the number was, maybe it was 3. And then we'd rerun the analysis again. So we get 2 different reliability coefficients because we have two different scales that we are working with. Brianna?
If you had a 2-item component and their correlation was 0.7 or above, can you do an alpha with the 2 items?
What most people do is report both correlation and alpha, or at minimum just correlation. Alpha doesn't make sense mathematically with 2 items, but some people have a preference for both of them, and I would report for 2 items, correlation and alpha. That make sense? So in our case, the reliability, much to my dismay, wasn't all that strong. What's a good number for reliability?
0.8.
Yeah, 0.8. What